So as a continuation from our previous case that we had working with the derivatives, we also have the reverse of what we have, which is actually the antiderivative, like what we had previously. You managed to differentiate with respect to x, a certain function, whatever that you're given, 5x to the exponent of 4, you managed to differentiate even the trigonometric functions with respect to x, where we are stating or where we are taking these from the standard functions. All right, from the standard functions, we saw that on the derivative, ax to the exponent of n is going to give us what? When you're differentiating something of this nature, so that we're going to drop the exponent, then we subtract 1 on our exponent on the derivative. So it was an x to the exponent of n minus 1. You drop the exponent, then you subtract 1. So in that same sense, we're using that. We're going to multiply 5 and this 4. So we're going to multiply 4 to 5, all right? So you multiply these two. That's 4 times 5, which is what? Which is 20. X to the exponent of what? We subtract 1, which is to the exponent of 3. That's the derivative. We're done. With respect to x, we have an x there. So you can differentiate. If it is a trigonometric, we saw that a sign, we just needed to know that a sign is going to give us a cos. Like I said, the proof or where we are going to actually apply these is in our N5. In our N5, that is where we're going to actually be working with the first principles to prove truly that the derivative of a sign, it's a cos. But in our case, we just need what are referred to as the standard functions, which we are also given in our formula sheet. So it is just like a follow-up method. Integration derivative is a follow-up method. You follow how you are given. All right. So as for our derivatives, we had this part, guys, as we're differentiating our standard, all right, from this, every part we explained as we had our classes. So I don't know if there's any derivative that we never explained, but everything was explained. So in our case, we are saying these derivatives, guys, can, just like the opposite now, to say we are moving from this side, going back to that f of x. You are given f of x, then you differentiated, all right? I want you to understand this because this is going to be part of our formula, this one, to integrate. We are saying the derivative, this part that we had before, all right? We are given as f of x. This is what? Our derivative. This is our derivative. We differentiated this with respect to x. So we are saying the opposite is supposed to be true. If we integrate this derivative, it is supposed to give us what? Our f of x original, the way that it was before. If we are to integrate, so this is the part of what we refer to as the indefinite integral, which is simply an antiderivative, an opposite to what we had, which is simply an antiderivative, opposite to what we had. So we are saying from that part, if we are to notice it properly, we are supposed to integrate this derivative to give us what? F of x. So we are saying the integral of that derivative, the first derivative that we have there. So this is the sign that you use for integration. That one is the integral sign. All right. So we are saying the integral of what? This derivative, which is our first f prime x, this one, the first derivative, if we are to integrate that with respect to x, so this one, it is simply dx with respect to x, with respect to x. It is supposed to give us what? The original function that we had, all right? Sorry for that. I want us to see here. The original function that we had, which is what? Our f of x. So this is what we are going to have. It is going to give us f of x, the original function, the derivative. If we integrate that derivative that we had before, we must get the original function which is our f of x. Then just because of some expressions that we have in our simplifications, remember in your derivative, if you differentiate with respect to x, a constant, let's say a number which is 2, you're going to get a 0. So just for the sake of those numbers, because we might not see that part where a constant was, because every constant, whether the constant is 10, the derivative will give us a 0. Whether the constant, so in that case, guys, whether it's a negative number, we do not know. For that case of the constant, which was being differentiated to give us a 0, we are supposed to put also that in mind to say there can be a constant. So we are supposed to say every part after integrating, we are supposed to add C, which is the constant of integration, representing those derivatives that were being differentiated to give us what? A 0, those constants. So this is the case, guys. This is our case of the indefinite integral, the antiderivative, the opposite to what we had. Opposite to what we had. So in this manner, guys, we are simply saying this is the first derivative. Remember, the first derivative can also be given like this. So you can also write in that same manner. Also, we can have it just like, what can we say? Guys, the presentation, there are so many different ways that you can have, but we simply have the integral of that part that we had differentiate to give us what? To give us our f of x. So if we are to say this is the, if you do not understand, guys, I'm not saying memorize this formula, this. No, 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 no. What I want you to know is that it is just a reverse. It's just a reverse that we have. So this is what we're going to have on our standard integrals, where we've got the standard functions. So let's focus on our standard functions and see what we are simply having. Remember, we had to differentiate, okay, with respect to x. Let's say we are given 3x squared. If we differentiate, remember the concept, you drop the exponent, 2 times 3, which is 6, then you subtract 1, you get what? 6x. So this concept, you're saying, this is the derivative, this one. This is our derivative. This is the f of x that we had, and we got our derivative. So we are saying if we are to integrate the derivative, this one that we see, which is 6x, with respect to x, guys, we are supposed to obtain exactly this f of x as it was, originally as it was. We are supposed to get 3x squared. But because we do not know, like, was it going to be a constant or what? We have to add the constant of what? Integration. So this is what you want to prove, to say, truly, this is the reverse. This was our first derivative, and this is our f of x, as we can see here, 3x squared. It gives us what? 6x. So we want to prove that if we are to integrate this, we are supposed to get us this part. So this is from the standard function. The first part of our standard function states that the integral of any part of ax to the exponent of n. Remember, we are integrating with respect to x. When you are integrating, this time, guys, whenever you're integrating, you add 1 on the exponent. So it's going to be ax to the exponent of n plus 1. You add 1 on the exponent. So it's n plus 1 over n plus 1. This is the concept that we're going to have now on our integration. So just like the derivative, guys, you are given this as your standard ax to the exponent of n. We're going to have as anx. You are given, follow that. That is why I was saying integration, derivatives, it's a follow-up. Don't try to bring something that you do not know. Don't even try that. Use all standard functions as you are given. So the lucky part that we have is we are given these in our formula sheet. In the case that we have what? Forgotten this part. All right, let's go to our formula sheet. This is how it's going to look like since it is not yet updated. Remember, we have the revised curriculum. So also our formula sheet is supposed to be revised, but it is not yet revised. So if we check on the integrals, This is the part that we have on the standard. They gave you every standard integral that you're supposed to use. So as long you can write, guys, as long you can write your question in this format, yeah, like this one, this ax to the exponent of n, like what we are given on that part. It's going to be what? Ax to the exponent of n plus 1 over n plus 1 plus the constant of integration. This is what we're talking about. So as long you've got a over x, as long you've got this, as long these are standard integrals that you need to follow. So it's like we don't get these from anywhere. To prove these, guys, it is the opposite. Like if you can be able to differentiate, if you manage to differentiate them, then this part is the opposite, just like that. Just like that, guys. Do not worry about integration, guys. You are scratching your head. Integration is difficult. No, integration is not difficult. The opposite. If you understand this concept from now, it must be easier. If it was difficult, now it must be what? Easier. So this is the concept. So let's apply this to integrate 6x, this one, and prove that it is supposed to give us exactly 3x squared. So here I just wrote the answer to say we are supposed to get that. So let's prove the integral of 6x with respect to x. So it must be x with respect to x. If it is of t here, it must be with respect to t. Just like what we saw on our derivative, with respect to what you are integrating there. So it's with respect to what? To x. So this is what we have. Originally, this x is what? 6x to the exponent of 1. We need to see the exponent. Originally, it is like this. So if we were to integrate, we were going to get what? The formula is saying that we are going to have 6x. A is the constant. A is the constant. It is the constant. It is not changing. It is the constant, this one, which is the same as our 6. So in our case, we're going to have what? 6, that is our constant, times what? X to the exponent. As you can see, on our exponent, we are adding 1, n plus 1 as it was. But we are now having what? N plus 1 as it was here. We're going to add. So it's 1 plus 1. So it is supposed to be 6x to the exponent of what? 1 plus 1. Remember, originally, there is a 1 there. Over what? The same exponent that we have here, n plus 1. The same, meaning to say our exponent here is what? 1 plus 1. We're going to use that. It's a follow-up method, guys. You have to follow. You are given the formula, follow up the presentation, know what n represents. Just like that. If you know that, guys, you're done. This is your integration. It's nothing much. That is our engineering, guys. We know that it's just like follow up. So this is going to be 6x to the exponent of what? 1 plus 1, which is 2 over 1 plus 1, which is 2, plus the constant of integration. So this was going to cancel 2 into 3 into 6, which is 3. So that was going to give us 3x squared plus c. Exactly this part that I wrote here to say we had differentiated 3x squared to give us 6x. So the opposite is true. The integral of this must give us 3x squared. So if you can prove that, you're done, guys. You are done. If you can know this part, you're done. So this is the integral that you're going to have as long as you've got this part. So you have to use this part in as much as you can. We saw in the derivative previously that if you differentiate a 0, it is going to give you, a constant is going to give you a 0 if it is any number. But in our integral, guys, it is opposite. The integral of a constant, if you're given k as a constant with respect to, if it is with respect to x, then we're going to have this as kx plus the constant of integration. So what am I trying to say here? If it is the integral of k with respect to t, with respect to, the constant that you're given is supposed to multiply what you're integrating with respect to. So it's going to be kt plus c. This is what I'm trying to say. So meaning to say that if I am given to integrate 2 with respect to m, with respect to m, what am I going to have? The answer is going to be 2m plus the constant of integration. The integral of -3 with respect to x, with respect to what? X. So it's going to be -3, the constant as it is, times x plus the constant of integration. That is how you integrate all the constants, the integral of a with respect to x is going to give us what? A is a constant. So that's ax plus the constant of integration. Remember, it's with respect to x. So this is how we're going to be integrating the constants of this nature. So that is it, guys, for the basic or standard integrals that you're going to have in our next class. We are actually going to look into other standard functions. As we are dealing with our standard functions, we're going to be working with the exponential and logarithmic functions. So I want you to go through a lot of questions which are of this nature to integrate maybe 14x to the exponent of 6 with respect to x, the integral of negative 3x to the exponent of 5 with respect to x, the integral of t with respect to t, the integral dx over 9 like this. When it is dx over 9, guys, what does it mean? It is simply this condition of our constant. Like they can just give us to confuse us, like this case. The integral, they put a dx on top like this, then a number. All right, remember in our numbers, 1 over 9 times 2, it is the same as 2 over 9. Why? This is 2 over 1. So you multiply the numerators together, denominators together. So this is the one that gave us 2 over 9. So if you take this into consideration, wherever we see this dx over, it simply means there is the coefficient here, 1 over 9. It is 1 over 9 separate. It is just like this, the integral of 1 over 9. Properly write it as so that you properly, this one, the constant, it's 1 over what? 1 over 9. The dx is just like times 2, this one, 1 over 9 times 2. It can be written on its own instead of us getting confused. It is just like a dx is separate like this. This is what it means. It's 1 over 9 times dx. So if you understand this, what is it? It's a constant. The integral of a constant with respect to x, 1 over 9, it's a constant. So what are we going to have? We are going to have 1 over 9. It's with respect to what? With respect to x. So it's 1 over 9x plus the constant of integration. You're done. You're done. So they try to confuse you guys, when you're dealing with questions. So just do as many questions as you can. And also, just like what we had on the derivatives previously, we saw that we're working with some of the functions under the square root. Get rid of those functions. And also, if you're given something like this, the integral of dm, just like this, the integral of dm, what does it mean? There is a constant here. The number is there, it's 1. Remember the integral of a constant. It's going to be constant times that with respect to what? So it's 1 times what? With respect to m. So that's 1m plus c, where 1m is what? It's simply m. So this is it. So this is the integral. So you're just given the integral. They just put an integral sign here. They write dx. There is a number there. There is a 1. So the answer is supposed to be 1x plus c, which is simply what? X plus c. Remember, when you integrate a constant, it carries what? X. So like I said, guys, do as many questions as you can. Where there are questions, let's communicate on the comment section. And also, guys, let's do understand that at Maison African Motives, we also have got the membership platform. And this membership platform, guys, is the one that is bringing this class to you. Not to say that you never requested, but most of you guys who are on public there, you don't even comment, like you don't even communicate. You just come and watch, you go, come and watch and go, come and watch and go. I'm not saying it's wrong. So we have to respect our members because they show that they are part of Maison African Motives, or those public subscribers, they show that they are part of Maison African Motives. Whatever that we do, we are supposed to bring their views first. If they have a topic, whatever that they need to be done, we have to bring that. So here is just like an introduction. So I needed us all to have the basic information, but other classes, do not be surprised to see them written members only or membership. It means those videos are specifically meant for the members. So for you to join, you just need to click the join. Look into the prices that are there for the membership, guys. It's very cheap. It's like money for airtime. I think it's very cheap, guys. Like a 1 week airtime, not 1 week, 1 day airtime. Guys, I don't know what can I say. If you don't want to join, it's fine, but it's very cheap. Anyways, let's continue here, guys. This is where we are. Whenever you're dealing with the exponents, also apply those laws of exponents. Guys, if you know how to differentiate this one is not supposed to give us problem because you differentiated something like this previously. So it's supposed to change because now there's an integral sign. No. We need to rewrite the same way that we had on those derivatives as long we are having ax to the exponent, this format. So this is what we have. What are you going to do? There's an 8 here on the numerator. Let's just leave it as it is because it's already on top. When I'm saying something is on top, I'm saying it's on the numerator. So something that is on top is just like a whole number, 8. Remember, 8 over 1, it is same as 8. If it is just x, it is same as x over 1. So something that is on top can be written the same way that you write your whole numbers because it represents a whole number. Anything that is on top. So this is what I'm trying to say. So this is just like 8 times this 1 over this part here. It's just like we've got 1 over the cube root of what? X to the exponent of 2 with respect to x. So this is just the integral of 8 times the cube root of, remember from our laws of exponents, x to the exponent of m over n. It will give us what? The nth root of x to the exponent of m. So this is what we have here, the nth root, the part here that we are seeing here, the nth root. So we just want to focus about this one, all right? Not the 1 over. Forget about this one for now. For now, forget about that one. We just want this part. So it means this was going to be what? This was going to be 1 over x to the exponent of what? We want to take this back. So it's m over n, 2 over 3, m over n, 2 over 3. So that's 2 over 3 with respect to x. So this is it. So we're going to have the integral of what? Of 8 times this x taken up to be written as x to the exponent of, just like this 8, a whole number. So we have to take it up. Remember, anything that is on top can be written in this manner. So the moment we take this x up to the numerator, it is just like a whole number. So it can be written just normally as x to the exponent of what? It does not just happen. You don't just throw it on top. There are laws that govern that. To bring it on top, what is going to happen? We introduce a negative on the exponent. So it will be to the exponent of 2 over 3, which is also the opposite to bring it down. We introduce a negative. To what is there? Introduce a negative. There was a negative. There was a positive on the exponent. So you put a negative. So the opposite is true. To bring it down, I just have to introduce what? A negative here. So a negative and a negative with what? Positive. It is now back to where it was. So you see. So this is the idea, guys. You just have to understand also your laws of exponents. We are in N4, but those exponents from N3, they still play a role. After that, we can now integrate. So you're going to integrate just like what we had previously. We said anything of this nature to the exponent of n is going to give us what? So that is going to be 8, which is our constant. So that's 8. X to the exponent of what? We're going to add 1 to our exponent. X to the exponent of negative 2 over 3 plus 1 over minus 2 over 3 plus 1. This is what we're supposed to write. But guys, let's not have a lot of things like written in this format. Yes, you can just write, but just simplify some of this. Just use your calculator. Minus 2 over 3. You were going to get minus 2 over 3 plus 1 was going to give you a third, 1 over 3. So this was going to give us 1 over 3. So definitely it means we are dividing by what? Same 1 over 3, because it is the same thing that you're going to have there. So we are dividing by what? 1 over 3. So this is what we have. 1 over 3, it's a number on its own. It's on its own, this part. We are referring to something that is on its own. So what are we going to do? we are going to simply evaluate. Okay, let us just bring our calculator. I'm forced now to have that calculator. So this is what you're going to just do. 8 divided to this one. 8 divided by 1 over 3. So it's 8 over, you can even put a fraction, 1 over 3 like this. Then close this bracket. So that was going to give us what? 24. So the whole part, if we are to divide this 24, this 8 divided to 1 over 3, this one, we're going to obtain what? A 24. This is our case. So that was going to give us what? 24. X to the exponent of what? A third. We are integrating. The moment we are doing this, we are integrating, so we must have the constant of what? Of integration. From this stage here, we started to integrate. So this is what we are having at the end. And it's a positive exponent that we are having. So we can just leave it like that. Whether you want to introduce those sets, we can introduce back the sets, just like what we had. Remember, this is simply as what? The cube root of x. Remember, it's supposed to be like to the exponent of 1, but the 1 there does not affect. So it will just remain as what? The cube root of x. So it's 24 times the cube root of x. So these are the typical questions that you just need to work on. Like I said, guys, do revise as many questions as you can. Know how to bring an exponent which is in the denominator, to bring it up. It carries a negative, or it just changes the sign of the exponent. That's the case. Just changes the sign. It's all about the simplification, guys. All that you can see now, it's all about the simplification, knowing your laws of exponents, simplifying basic mathematical terms, knowing just mathematical terms. But the part of the integration is this one. So this is the first part of our standard functions. We're going to meet in another class, working with the exponential logarithmic functions. Till we meet again.